So as Bhavna said, today is a World Water Day, and there cannot be a better occasion than this to speak on water efficiency, energy efficiency. And thanks AE for the opportunity. As we all know, sustainability is a big challenge and a task before all of us. And the data which is available in the public domain already shows in last 50 years how the global warming is affecting the humanity. If you look at the left-hand side picture, you can see everywhere yellow, green, and orange. That means the temperatures have gone up from, let's say, 0.5 degrees C to up to 4 degrees C in various regions. And this all started, after the Industrial Revolution. Let me pick up the pointer. And in last 50 years, you can see here the increase in the CO2 concentration or carbon emissions are from 250 ppm to 400 ppm, which is phenomenal. And it's an exponentially, it is increasing. And if we cannot stop this, there will be a lot of issues as far as the liability is concerned, and we'll have to face them. So it's time now to act, on the sustainability. Another challenge that we are facing is, of course, water scarcity, right? Although Earth has got 70% water, everyone says 70% water on the Earth. But if you look at in realistic way, only 3% of the world's water is a fresh water, okay? And out of that, 2/3 is already tucked away in frozen glaciers. That means only 1% water, fresh water is available for us for using it for various purposes, right? And another information from this worldwildlife.org is 2/3 of the world's population may face water shortages by 2025. So it's not far, right? And 2.7 billion people already, they find water shortage for at least 1 month in the year. And over 1 billion people don't have access to the water. So it's high time for all of us to focus on the water savings, and we need to look at water savings beyond the ROI. And these emissions, or you can say sustainability, is very well linked to the buildings, because buildings are consuming a lot of energy and water. If you look at the data, building sector consumes 40% of the global energy, okay, which is phenomenal, and 25% of the global water. And it emits 1/3 of GHG emissions, and it contributes to the largest, you can say, one of the larger contributor to global GHG emissions. And we cannot stop here, right? The buildings are growing day by day. So, building sector is going to consume more and more energy, more and more water. So it's high time we need to act on it and try and see how can we reduce the energy and water consumption, right? When you look at the energy consumption pattern in buildings, so over 50% of the energy is consumed in HVAC. So that's phenomenal, and there exists an opportunity to cut down the costs and to save money, as well as the emissions and water as well. In a centrally air-conditioned building, mainly, let's say in the weather like India, we have mostly water-cooled chillers, because water-cooled chillers are efficient, okay? That's where most of the places you'll find that water-cooled chillers are installed, and if there are water-cooled chillers, we have cooling towers attached to it, right? So the combination of these two will treat, the air, and that's where we get the cooling in the buildings. And we have condensers here in the chillers. The solutions that are quite helpful for energy and water saving are automatic condenser tube cleaning system. It is also called as ATCS, and electrolytic water treatment system. Both these solutions are chemical-free solutions and environment-friendly. Let's talk about the first one, which is automatic condenser tube cleaning system. It's basically an online system that helps to keep the condenser tubes clean, because when water is passing inside the condenser tubes, because of the heat transfer in the condenser and the water contains calcium, magnesium salts, there will be deposition of salts or scale inside the tubes, okay? And this system works on the cleaning balls. The balls are injected and collected back, and that's how the cleaning happens with the help of these balls. And there's a potential to save up to 20% energy in HVAC water cooled chillers by using sponge type condenser cleaning system. Let's talk about the problem. What is the problem in the condenser? As I explained to you, there are magnesium and calcium bicarbonates present in the water. When they react in the condenser with the heat that is exchanged, there is a precipitation of magnesium carbonate, calcium carbonate, which will deposit, inside the tubes. And that's where you will have an impact on the efficiency because your heat transfer will not be proper. And the problem of skilling will be severe or less severe depending on the water qualities that is maintained at various places. If you look at the impact of skilling or fouling on the condenser or evaporator, the first impact is it reduces the heat transfer coefficient on the heat exchangers, in the heat exchangers. The moment we have this, it will reduce the cooling capacity of the chillers, okay? So you don't get, a proper cooling. Rather, suppose the chiller is designed for, say, 1000 TR, you may not get 1000 TR cooling if the condenser is fouled. And the specific power consumption increases by up to 20%. It depends on, what is the extent of fouling and, how the condenser approach is at what value. Depending on that, you will have the potential to save here. Also, the compressors of the chillers need to work at the higher discharge pressures. And that's where it affects the compressor life as well. And then regular practice is to stop the chillers periodically. Could be 1 month, could be 3 months, could be 6 months, 1 year, depending on the scale forming tendency of the water at various industries. This is a simple graph which all of us being engineers have studied, in the college. It's a pressure enthalpy chart. Okay. Now I'll try to explain here how scaling or fouling impacts the efficiency of the chiller. Okay. Now this 1 to 2 is heat removed from the process or from the space. That is called evaporator. 2 to 3 is compressor. Right, the gas will be compressed by the compressor to point number 3. 3 to 4 is heat is rejected to atmosphere, that is maybe condensers, right? And 4 to 1 is expansion. So this is your standard cycle of refrigeration. Now, as there is a scaling inside the tubes, you will find that the discharge pressure is increasing, right, from 3 to 3 dash. Now, the moment there is fouling, you will find that this curve has shifted from 2 to 3 to 2 to 3 dash, and when you project this line on the pressure enthalpy curve, it will hit at 4 dash. In the previous case, when the condenser was clean or new, your cooling capacity was this, right here. So it is larger. The moment there is fouling inside the tubes of the condenser, your cooling capacity has dropped to this red line, right? Simultaneously, what has happened is as the compressor pressure has increased, compressor will draw more power from 3 to 3 dash, right? So you might have, let's say, 100 kilowatt here, and 3 dash could be, let's say, 120 kilowatt. So in short, your power consumption has gone up and your cooling capacity has gone down. And therefore, there is a reduction in the COP, that is coefficient of performance. That means your IKW per TR has gone up. This is another, simple, you can say, graph which shows how the scaling thickness affects the power consumption. So you can see the impact of the scaling here. So 1 millimeter of the fouling or scaling can increase the specific power consumption by almost about 30%. So it's all the way important, to avoid these fouling or scaling in the condenser tubes. Let's look at TCO, or total cost of ownership, or also called as life cycle costing of a water cooled chiller. Your 85% of the cost in the life cycle of the chiller is energy cost, energy consumption. Okay, 10% is investment and 5% is operations and maintenance cost. So there exists a large opportunity for us to attack on this pie and save, right? Even a small savings on this big pie can make a substantial difference in terms of money, in terms of energy, and in terms of emissions. All. Now, this is a typical example for a screw chiller. Here, I'm trying to explain how the condenser approach, increase in the condenser approach, is affecting your kilowatt per ton, okay, IKW per TR, in the fouled condenser. Now, here, if you see, if your condenser approach, when it is new, it is about 1 degree C, and if your IKW per TR is 0.7, as the approach is increasing, your IKW per TR is going up, right, up to here. And in many industries, I mean, we see this 5 to 7 is a normal condenser approach when the condenser is fouled, okay? Now you can imagine the energy loss that is taking place from this point to this point, okay? And this is the time here, okay? What we are losing is the area under this curve. If we are able to avoid this triangle and keep this flat like this, you will save all this energy. Now this is possible with the technology. This is online condenser tube cleaning system. It's possible to maintain approach between 1 to 2 throughout the year by using ball type ATCS. So based on our experience, we also opened the condenser tubes after 1 year, 2 year, 4 year at various sites. And we found that the condenser tubes are quite clean here. And that's where the condenser approach is maintained, okay? And it has improved substantial energy efficiency in the water-cooled chillers. This is another example wherein we found the tubes clean even after 2 years. This one is one of the IT companies. Even after the 4 years, the condenser approach was maintained below 1 degree F. See, the key for this technology is we need to maintain the cleaning sponge balls in the system in circulation. Okay, then we don't have to look back for manual cleaning of the system. Many times after these systems are installed, people neglect changing the balls, and that's where the scaling again can happen. This is just one example I am trying to show here. We have some more case studies, at the end of this session. We'll run through that as well. Here it is clear, we are seeing here the chiller number 1, for example, your condenser approach is maintained at much lower values compared to when it was before descaling. When we look at the benefits that this system offers by keeping the condenser tubes clean online without any shutdown, is up to 20% energy saving in water-cooled chillers. It will improve the cooling capacity of the chillers. It will also improve the condenser tube life, because as the tubes remain clean, there is no deposition of scales inside the tubes. That's where the corrosion is also reduced. You will also improve the life of the compressors, because the compressors will run at steady pressures. Okay, and you can avoid the costly shutdown and downtime, which is very important for buildings. I mean, let's say hotels or hospitals, wherein they have to run chillers continuously, so they can't afford to take shutdowns or downtime. It eliminates the offline cleaning of the condensers, and with all these benefits, if you see, this technology has proven in the market for over so many years now, and payback offered by these systems are about 1 year to 2 years. It's very attractive financially as well. These are some of the typical installations wherein you will find there is a skid, there is a ball trap, and there are ball collectors. It's a very simple installation. It's a simple technology, but very effective. So on this, here you will see that one skid is able to manage multiple condensers. Like individual chillers will have the ball trap and ball collector, so that the ball set is individually separate for each chiller. So that's to save on the costs, capex. The second technology that we are talking about now is the electrolytic cooling tower water treatment system. Okay? This is again a chemical-free solution that is helpful for treating the cooling tower circulation water, which will it's basically based on the electrolysis of the water. It removes the scale from the cooling tower sump water, and that's how we're able to save up to 80% blowdown water consumption. This is the cooling tower, and this is installed in the side stream. The green color chamber that we are seeing here is electrolytic chamber, so where the electrolysis takes place. The blue color vessel here is nothing but a dual media filter. So this takes care of suspended solids, removing the suspended solids. Here, the treatment of the circulation water takes place. I'll explain you in the next slides how this really works and what are the reactions that are happening inside this. This is the control panel which controls all the system operations automatically. When we look at the challenges that we have in the cooling water circuit, is mainly corrosion, scaling in the pipes. Then we have scaling on the fills, algae formation on the fills. I mean, almost everywhere you'll have this kind of problems in the cooling towers. It could be severe, it could be less severe, depending on, the water quality that is maintained. If you look at the impact of the scaling and algae formation on the cooling towers, it will reduce the cooling circuit efficiency overall. It also reduces the cooling tower efficacy. That means you don't get proper delta T. And it increases the cost of operations and maintenance, because then you have to clean the cooling towers frequently, you have to maintain, you have to replace the fills, etc. The problem with the cooling towers is there is a continuous evaporation happening in the cooling tower, which is a natural process, right? Because we are cooling water from high temperature to a lower temperature, bringing it down to a lower temperature by using the evaporation process. So in that process, there's a continuous evaporation that is happening from the cooling tower. And that's where the TDS of the water in the sump goes up. And as this water is getting circulated in the condenser, okay, there is apparent tendency of scale formation in the condensers and in the pipes as well, okay, and also the cooling tower fills. And then we need to add a makeup water, because there is evaporation, and also because we have to maintain certain TDS levels or conductivity levels in the cooling towers. There is a blowdown that is happening. Sometimes it is continuous, sometimes it is intermittent. Okay? So the blowdown is must when there is evaporation and we have to maintain certain parameters inside the cooling towers. So impact of all this is mainly increased water wastage, okay, which we cannot avoid. High level of chemical consumption, because this water needs to be treated by chemicals. Replacement of fills periodically. So fills replacement cost is there every, let's say, 2, 3 years, 4 years, depends on the water quality. Conventional methods that are used are basically the offline chemical dosing, which is done in the cooling towers, that uses antiscalants, corrosion inhibitors, and biocides. So here the dosing is done manually. So there are cans like this, you can see everywhere near the cooling towers. There are some systems which are skid mounted, but chemical dosing, which is online controlled chemical dosing. So there is a skid, there is a controller, there are some sensors to control the conductivity or the TDS of the circulation water, and accordingly, the chemical dosing is done in the proportion. Okay? It's the controlled chemical dosing. The third method that is used is uncontrolled online chemical dosing. So you will have tanks like this, and then you have the metering pumps. You have a small control panel to control the operation of these pumps. But here these pumps will operate continuously, dosing pumps, and pump the chemicals into the cooling towers. Then we have electromagnetic non-chemical devices and ultra-frequency non-chemical devices, which are not proven to be very effective, when it comes to the applications. Let's look at the drawbacks of conventional water treatment methods. The first and foremost is high operations and maintenance cost. Okay. Online controlled chemical dosing has got high initial cost as well and operating cost as well. Okay. Plus, there are safety issues also, because this chemical needs to be handled, and the chemicals are hazardous. Sometimes they are using acids, and handling is really a hazardous task in the industries. So to maintain the parameters in the cooling water sump, there is high blowdown that needs to be given continuously. The above treatment methods are not environment friendly, because we add chemicals and we do the blowdown, to maintain the TDS or conductivity in the cooling tower sump. And the effectiveness of non-chemical devices are really questionable. So such a technology called electrolytic water treatment system has been very effective to control, let's say, the parameters in the cooling tower, and also to avoid the chemical dosing, reduce or avoid the chemical dosing in the cooling towers, and also improve the water quality of the cooling towers. I'll show you in next slides how water quality is also improved. So as I explained to you a couple of slides back, so this is how the system will look from the front. So there's an electrolytic reactor, control panel, power supply, and here is the dual media filter. And then we have control panel will have certain elements like automated self-cleaning mechanism, okay, to clean this reactor periodically, so that we don't need to open this reactor manually for cleaning. Then we have pH and conductivity sensors to monitor these parameters online. So a lot of these facilities are available by various vendors in the market. Let's look at the principle of operation of this technology. First and foremost is here we have anodes and cathode, in this reactor, green chamber. So once we give electricity or power supply to anode and cathode, we generate OH minus ions. The moment we do this, we will have a separation of calcium, magnesium in the water, and they will try to migrate to cathode, which is negative electrode. Okay, and simultaneously we generate chlorine gas from the chlorides in the water at anode. So these are the steps. First step is we generate OH minus ions at the walls of the cathode here, and the middle ones you see here are anodes. Right. The moment we have OH minus ions, there is deposition of calcium and magnesium and other plus ions which are contributing towards TDS. They will get deposited here on the walls, and we generate chlorine gas from the chlorides already present in the water. So there is no chemical that is required, for generating chlorine. These are the electrochemical reactions that happen inside the reactor. So there's a primary anode reaction where oxidation of water takes place. So oxidation means water will lose the electron. So twice H2O will lose the electrons to generate O2, oxygen and H plus ions. The second reaction is primary cathode reaction. So as there is a primary anode reaction, simultaneously there is a primary cathode reaction happening, which is reduction of water. Reduction means gaining of electrons. So these electrons liberated here at anode will be gained at cathode by the water to generate H2 and OH minus ion. And generating these OH minus ions is the key for depositing the scale inside the reactors. Then we have a third reaction called secondary cathode reaction, where calcium bicarbonates will react with OH minus ions, these ions at cathode, to precipitate calcium carbonate, magnesium hydroxide, magnesium carbonate. So in the form of these elements, these calcium magnesium ions will get precipitated. And along with this, even other elements are getting precipitated on the cathode. I'll show you the analysis in the next few slides. Like silica also is getting removed. And the fourth reaction is secondary anode reaction, where chlorides, which has got negative charge, will be broken down into chlorine gas and electrons. So this chlorine gas will act as biocide to kill the microbes. So along with the chlorine, also H2O2 and O3 oxidants are generated in the process, and that's where these reactions or the process can be used to control the microbial count, algae formation inside the cooling towers. Let's look at the benefits this kind of technologies offer, electrolysis-based technologies offer. Of course, it's a zero chemical technology. It reduces blow-down water consumption by up to 80%. It will reduce the corrosion in the condenser pipes. It extends the life of cooling tower, means your frequency of changing fills will reduce. Results into energy saving. Now, you must have seen in many industries or even for the buildings nowadays, there is a requirement of zero liquid discharge, or at least we have to treat the water, and you just can't let the water down like that into the drain. So there is a lot of energy cost involved, in ZLD plants. So once we save the blow down water consumption, ultimately there will be a saving in the energy cost. Okay. And the blow down water can be used for gardening because there are no chemicals in the blow down water. So in fact, if you look at this, truly you can achieve ZLD if you have a garden there and the water is required for gardening. There are some systems available, for the larger cooling towers where the flow can be, let's say, 3,000 metric cube per hour, mainly for larger industries. So this is a typical installation in a petrochemical plant. I'll just brief you on this and then we'll move on to a case study on building as well. Okay. If you see here, let's say December 21 onwards is what it is with the electrolytic system it is running. So if you see here, pH is maintained, total hardness is lower than what it was before. Even the TDS is lower than what it was before. Okay. Even the chlorides, you will observe that the chlorides are also reduced compared to what it was before. Even the silica has got a downward trend from here. These are some of the parameters before and after implementation of electrolysis-based water treatment. If you look at, let's say, TDS, circulation water TDS, which used to be about, on an average, 1200 plus, is now about 1000, okay, or below that. And even the hardness, total hardness, which used to be about 700, for this particular case, it's operating at about 550 on an average, 500 to 550 in that range, right? So you can see a clear improvement in the water quality as well, by using this technology. Even the silica here was in the range of about 120, 140 like that. It's now about 80, 90 in this range. This is what, the scale that is removed from the water. This is how it looks like. Okay. Because it's automatically cleaned and then we need to collect this for sampling and checking it for the, analysis. So this is the analysis that we did, for various elements in the scale. You can see here, calcium is there, magnesium is there, silica is there, sulfate is there, iron is there. orthophosphates are there. So that means all these elements are removed from the water, and that's how the water quality has improved. Plus, there is a blowdown reduction, substantial blowdown reduction. So in this particular case, almost the blowdown was 46 metric cube per day before implementing electrolysis technology. And after implementing this technology, you can see the parameters before and after was like I told you 1195, so around 1200 TDS was down to about 1000. Total hardness from around almost 675 to 550. Chlorides 548 to 329. And blowdown has reduced from 60 meter cube per day to 11.6 meter cube per day. Okay? And of course, LSI and other, let's say, water parameters have improved, and they got a lot of benefits on the process side. So the actual blowdown is about 11.6 KL per day, which is almost 81% reduction in the blowdown water consumption. And they saved almost 84 lakhs since December 21. This is another large installation for a 6,000 TR cooling tower. You can see here the cells are quite big. Okay, and this system is treating it. And when we say blowdown reduction, it's a measured blowdown reduction. We have here a flow meter which will measure the blowdown, actual blowdown that's happening from the system. Here also, we could see that pH is maintained, TDS is also maintained at desired levels. So in this particular case, the requirement was to improve, to reduce the TDS from 2100 to below 1500, which is achieved by this system. And there's almost 50% reduction in the blowdown water consumption also, which was 58 meter cube per day. Now it's about 28 meter cube per day. So this technology is quite promising, to reduce the water consumption substantially, mainly blowdown water consumption substantially. And this also has got an impact on the energy efficiency improvement of the chillers, because as we improve the delta T in the cooling tower, your energy consumption by the chillers in the buildings will also improve. This one is one of the installation at, you can say, an IT office, wherein this system is installed, and they got substantial reduction in the blowdown water consumption. So I will cover this as another case study, after which, after this presentation, I will project that case study. Another important parameter is Legionella. When we talk about cooling towers, people are concerned about Legionella. And with electrolysis technology, Legionella cannot exist. So we have done the test for that as well. Another important slide for algae formation, you can see here, algae formation is reduced drastically from before case and after case. Thank you. This was all about the presentation. Now I will switch over to case studies. Okay. Is it visible? Screen is visible?
Yes, it is.
Yeah, okay. This is for an office wherein the challenges were high cooling costs, high water consumption, and high chemical treatment costs. So this is the system that is installed on the terrace besides the cooling tower. Here, if you see, this blue line is before, and this is after. Okay, so the 8.5 pH and 8.2 was the makeup, right? Circulation was 8.5. Here the makeup pH was 7.6 after, I'm saying after case. And now it is circulation is maintained at 8.2, okay, which is in the range. Even the TDS, which was about, this is for circulation water TDS I'm talking about. Makeup was 762. Circulation was about 2600. And here, makeup was 650. And the system was able to maintain 1900 as the TDS. Okay. So 2600 to 1900. Same thing about TH. Earlier it was 90 in circulation water, now it's about 38. Okay, so there is, you can see a clear improvement in the water parameters. Even the chlorides, makeup water chlorides were 161 and circulation water was 269. But here the makeup water chlorides were very high. In spite of that, the system was able to maintain it below 500, it is 352. This one is the economics, wherein before and after case. So pH was maintained without and with, right? So 8.5 to 8.2. TDS is 2600 to about 1900. Total hardness, 90 to 38. Blow down 55 meter cube per day to 15 meter cube per day. So there is almost 70+% reduction in the blow down water consumption. And they were consuming almost 2.4 lakhs per month as the chemical cost, and now it's zero. So there's substantial benefit as far as chemical consumption or chemical cost reduction is concerned, and the blowdown reduction is concerned. So overall, they saved almost, they're saving rather 31.6 lakhs per year. Total savings, for water saving, and for chemical consumption, it's 29 lakhs per year, and total savings of almost about 60 lakhs per year. So these were the key benefits from this system for one of the office buildings. We'll quickly run through one of the case studies for the chillers as well, for automatic tube cleaning system. So this study was conducted way back, about I think couple of years back, 5-6 years back, and for a 200 TR chiller, wherein investment was about 6.5 lakhs and savings per year was 5.6 lakhs. So payback of almost around 1 year in this case. So this was the actual cooling load before, that is 163 TR. After was 173 TR. Power input was 112.6 kilowatt, and after was 111.5 kilowatt. And specific power consumption was 0.7 to 0.64, which is now corrected to CW inlet, because CW inlet before was 84.2 and after was 85.7. This is Fahrenheit actually, this is not correct. Okay. So you can see a clear difference of almost 10.57% in the IKW per TR by using automatic tube cleaning system. This is installed on a train chiller. And these are some of the trends that we plotted: kWh versus chill water temperature. Then kW per TR versus chill water temperature. This is TRH, that is cooling generated versus CW inlet temperature. Again, kilowatt versus CW inlet temperature. And this is the backup data wherein we had installed a data logger there for measuring all these parameters. Okay, chill water in, chill water out, then TRH, kWh, and that's where we monitored, here the IKW per TR. So on an average, if you see below, so this was before 0.7 was before IKW per TR. After was 0.64. Okay, this is the log data. And there is one case study for the hospital also, wherein again the payback was less than 1 year for this hospital for 2 into 500 TR chillers, around 10% improvement. So these are some of the trends. We plotted discharge pressure versus cooling water inlet, this amperes versus cooling tower inlet temperature, etc. This is percentage load versus IKW per TR, load versus IKW per TR. So this is after. You can clearly see a difference of IKW per TR before and after implementation. This was a condenser approach, load versus condenser approach. So after implementation of automatic tube cleaning system, these red ones, so it's about below 1 degree F roughly, and before was it used to go even up to 7 degree F. So this is how they have saved substantially on the energy costs. And this is the backup data we have for it. So I think we have a lot of case studies. One more case study is for the bank, wherein again it was about 1 year was the payback. Okay, about 18%, let's say, improvement in the IKW per TR. And this is the backup data for the improvement. Both these technologies are now proven, let's say, in the market, although they are innovative and proven, and they are offering an excellent ROI for the customers. Okay, and also addressing the sustainability. So that's all I had to say. And now we can take up some questions, Vana, if needed.
Yes. Thank you, Mohan. That was a great presentation, and case studies are also very effective, resulting into great savings. We have questions, and the first question is from Zairus Dias. What is the effect of balls getting stuck in condenser tubes? Would we require to still do condenser descaling as balls get stuck? And what will be the effect of pressure across the tubes after installation and its effects on efficiency?
Okay. Yeah.
By the way, people are clapping a lot.
Yeah, thank you.
Presentations. So that's great.
So for this, let's say I would answer briefly, because this system, when we commission now, or this system when it is commissioned, we need to do a proper descaling, and this tube needs to be checked thoroughly for cleanliness. So once we do that properly and commission the system, the balls don't get stuck inside the tube. And another important point is every 3 months we have to change the balls. Now, if you don't change the balls after 3 months, then there is a possibility that the balls may get stuck inside. So if you follow the proper guidelines from the manufacturer, we don't see any issue as such, balls getting stuck inside. Because I have seen these systems working in the field now for over 10 years. And there are installations wherein 4-5 years, no descaling was done.
Okay.
Hope I could answer the question, right?
Yeah. Yes, Mr. Jairus, I think your question is answered. And again, another question is from Ravi Anand Raje. He says, what can be the best practices for centralized VRF system as you specified for chiller plant?
Okay, now centralized VRF systems, if they are water cooled, then I mean the second technology I talked about, electrolytic water treatment system, can be useful, because in that case, once we remove the scale, ultimately you will get benefit, on the efficiency gain also. Otherwise, this online tube cleaning system may not be feasible, or it's not possible rather, because it's a VRF system. Okay, that's only used for a centralized chill water system.
I hope that answers your question, Mr. Raje. And now Mr. Amitabh says informative presentation and please share contact number. So I have already shared phone number and email address in the question answer box.
Okay.
Yeah.
Okay. Next.
And like if you have any further queries, you can contact us and we will connect you to Mr. Mohan. Yeah. Sure. And what is the Mr. Vaibhav is asking, what is the cooling tower electrolyzer electricity consumption?
Yes. Say for example, it depends on the cooling tower capacity. If let's say, just for your understanding,
Mohan, can you just excuse me? So sorry to interrupt. Can you just stop sharing because the double screen is appearing?
Okay, sorry.
Yeah, that's fine.
Yeah, that's okay. Yeah, it depends on the cooling tower capacity. Just to give an idea, for 1000 TR cooling tower, the consumption would roughly be about 2 kilowatt. Out of that, 1 kilowatt is for electrolysis and 1 kilowatt will be for the pump, circulation pump. So total 2 kilowatt for 1000 TR.
Okay. Yeah, Vaibhav, I hope that answers. And Mr. Kazi has question, is it effective in higher TDS water in cooling tower more than 40,000 TDS?
Oh, okay. So, I mean, is it seawater or, I mean, I'm not sure, because 40,000 is like a seawater.
Yeah, I think I will enable him.
Yeah.
Question. I'll enable him to talk and we can take that later also. Yeah.
I mean, so far, I mean, this technology has not been effective for such a high TDS.
Okay.
To me, it looks like it's a seawater.
Okay. Yeah, Mr. Kazi, you may type or I'll enable you to talk after one question. Now again, Mr. Ravindran has a question. With this, we have already covered. Right. Yeah. Mr. Gaurang Kumar Sharma, he is asking, sir, how is it different for electromagnetic and static water conditioner made by Vulcan? Is it working on electrolysis principle? Then how much electricity consumed and replacement cost of anode?
I think we missed one question, right? When you started, you talked about bicarbonate scales. Yeah. In your talk, but none of the slides showed the reduction in the carbonate scale, right? Post installation, what is the reduction in the carbon? What is the reduction in the carbonates? And yeah, I mean, if you look at carefully, when I have shown this slide of the scaling, it has got all these calcium, magnesium, right? Carbonates means when it precipitates in the form of calcium carbonate and magnesium carbonates. I don't know if you have noticed in that slide, wherein I had shown the analysis of the scale. It's already there. Okay, so let's move on.
Mr. Birla, like if you have any further questions, you can contact Mr. Mohan.
Sure, I'll be happy to address that.
Yeah. Then Gaurang Kumar Sharma is asking, like, how is it different from electromagnetic and static water conditioner made by Vulcan? Is it working on electrolysis principle? Then how much electricity is consumed and replacement cost of anode and cathode?
Yeah, so I'm not aware about exactly what Vulcan does, but the question that you asked is electromagnetic and static water conditioner, right? So this technology is very different. Electromagnetic is different, static water conditioner is different, and what the electrolysis technology is based on anode and cathode. Wherein they will actually break the salts and remove scale and solids from the water, which electromagnetic technology cannot do. That's the major difference. Okay. And by maintaining the same water parameters, it's possible to achieve the reduction in the blowdown water consumption by electrolysis technology. And regarding your question on anode and cathode, anode needs to be replaced after 5 years. Cathode need not be replaced.
Yeah, Mr. Sharma, I hope you got your answer. And now Mr. Raghavendra Sharma Mishra is asking, how will system control pH 7 to 7.5, whether additional acid dosing is required or not in cooling tower?
Okay. So, this is a specific question related to even, the makeup water quality. We need to know what is the makeup water quality. And based on that, it will be commented. And normally the range expected is 7.5 to 8.5 for the pH in the cooling tower circulation. Okay. That's what is better for as far as LSI is concerned. So if you can share the makeup water parameters along with this, so I'll be able to comment in more details, on this question.
Yeah. So, Mr. Sharma, Raghavendra Mishra, you can get in touch with Mohan, or you can contact us so that we can connect you to Mohan. Yeah. Now, Nehil Gupta has a question. Electrolytic handle up to what TDS?
This system can work up to 10,000 TDS in the cooling tower circuit. It has been tested up to 10,000. But for the condensers and all, typically in the industry, they maintain 2,500 to 3,000 maximum. In some industries where there's a problem of the water, they use groundwater. So there it can go as high as 10,000, what he's saying, sometimes.
Then Mr. Sudan, yeah. Yeah, Mr. Sudan is asking, is it necessary to install both ATC and electrolyzer for WCC?
Water cooled chillers, right? Okay. So ideally, yes, because the job of ATC is to keep the tubes and guaranteed cleaning of the tubes to maintain the condenser approach. Okay. And this electrolysis system is used for replacing the chemicals or reducing the chemical consumption or eliminating it, and also reducing the water consumption. So ideally, yes. So if you want perfect effect, both of these are important together.
Okay. Yeah. Hope that answers Sudan.
Yeah.
Then Raghavendra Mishra has another question.
Yeah.
How much chlorine gas will generate in electrolytic system during the process, as we have to maintain FRC level greater than 0.3 ppm in CT?
Okay. So this will depend on what is the concentration of the chlorides in the water. Okay. What we have observed is in the industries, if your TDS is below 2000, we can maintain up to 0.2 ppm of FRC. Okay. But this FRC is required to keep microbial count below certain limits, right? Even with lower FRC levels, it is possible by this technology to keep the microbial count, that is TBC or TVC, within the limits. Unless there is a guideline from any of the authorities to maintain 0.3 ppm FRC levels.
Yeah.
Cost and life of cathode anode. Life, I think already I answered. The cost will again depend on the capacity. Typically, you can say 30 to 35% of the equipment cost is the cost of anodes.
Yeah. So then another question from Mr. Birla is, what really happens by electrolysis of water? Does all scales are removed in the system? How much is the maximum distance expected from the cooling tower of this installation?
Yeah, number one, it cannot remove the 100% scale, right? So typically, there are two things. We remove the scale up to 50%. If we want water reduction, then what we do is we maintain the similar parameters, what you are right now comfortable with, and then reduce the blow down water consumption, number one. Number two, if reduction in the parameters is needed, then so in that case, reduction in the parameters is needed, then we cannot achieve the blow down. So it is either or. To answer your question in short, is about 40 to 50%. Yeah, we can remove. And the second question he had was how much is the maximum distance? Distance is not a problem, up to 20, 30 meters is not a problem, because it's just the piping that we need to run from cooling tower to the system, and the system is working in the side stream.
Raghavendra Mishra has another question. How will electrolytic system control corrosion in cooling tower?
Yeah. So
less than 2 ppm.
Yeah. I mean, if you see after electrolysis, the water is towards alkaline, so it is less aggressive. And that's where the corrosion is reduced by electrolysis system. And also the existing Fe content, if it is there, it will be reduced because it will deposit on the cathode.
Yeah.
I hope I could.
Yeah. From electrolysis, Mr. Amitabh says, from electrolysis, hydrogen will also be produced at cathode. Yes. Please explain.
Yeah, already in the reactions I explained, hydrogen is produced, but that is in a much, much lower quantity or much lower than the LEL levels. Okay. It's the byproduct. You're right. It will be produced. But the quantity is very low, much below LEL levels.
Okay. Then electrostatic water conditioner is effective or not? Again, Gaurang Kumar is asking.
So I really can't comment on this. But I mean, whatever I have seen, such kind of technologies, most of them are non-functional, I'll say. And next question is, I think, which material is used for anode? So every manufacturer will have its own proprietary technologies and material for anodes.
And again, Mr. Mishra is asking about chlorine gas generation.
How much chlorine gas is that? I already answered this, right? I think it's a repeated question.
I think we have, this question is repeated. Yeah. So that was a quite patient answering, Mr. Mohan. Lot of questions today. It means it generates so much of curiosity of all the listeners. Thank you so much.
Thank you.
Let me acknowledge presence of our regional director of AEE Asia. And can we have 2 words from you, Mr. Binoy? Mr. Binoy, I have allowed you to talk, and so can we have 2 words from you regarding our sessions and AEE activities? I think we are not able to reach him, I suppose. Anyways, we'll have a word with him next time. Yeah. Thank you so much, Mohan. And thank you all the attendees for joining us. And extremely sorry for the glitch that was for some of you regarding the link. and it was wrongly posted. The link was wrongly posted, and we have tried our best to reach to all of you and make you a part of this webinar also. And hope you keep continuing attending our sessions. And like, if you have any feedbacks and suggestions, we are always open to that. And if you feel that you want to present something on this forum, do contact us so that we can evaluate, our committee can evaluate it and give you an opportunity to present on this forum. Thank you so much for joining. Thank you, Mr. Mohan, once again.
Thank you, AEA. Thank you, everyone. Thank you very much. Bye.